Oh, jeez. Try again. There we go. All right. So let's make a graph. 0, 0. We've got a point at 0, 0. So 0, 4, and 8 are our x-coordinates. And then 0, 2, and 4 are our y-coordinates. So at 0, 0, it's 1. At 4, 0, it's 2. Let's do a different color. And at 8, 0, it's 3. And then at 2, 0, 2, it's 2. At 4, 2, it's 4. And then what's this? 6. This is 8, 2, that's right, 6. And then 0, 4, 4, 7, 11. So what do you notice about the graph compared to the table? It's like opposite, right? So you can't look at this and think lower right, upper left, because they're making y go downward, right? This greater y's go down. So we need to make this graph to see, and they want us to use lower left and upper right, and then average. Okay, so these are the rates, right? This is the mosquito per square meter. And so if we use lower left, so we could call this like 1, 2, 3, and 4. Lower left would be this way, right? And how many square meters is each dA? 4 times 2 is 8. It's 8 square meters per dA, is that right? So then if we do lower left, it's going to be, our first one is going to be 1 times 8, then plus 2 times 8, etc. Plus another 2 times 8, plus 4 times 8. And what is that? 32 plus 64, 72. Check my math. And then the upper right, we're going to go up this way now. And use those rates, right? Use those rates as what? As the so this 4, we're going to say is the constant rate for that whole dA right there. And this 7 is going to be the constant rate for that whole area right there. So it's going to be 4 times 8 plus 2 is 6 times 8. Is 72 right, by the way? Thank you. And then 7 times 8 and 11 times 8. Gives 324. Thank you.
224.
2. Thank you. All right, 224. And so that's evaluating. So what is 72? That's saying that the total number of milligrams using the lower left, the total milligrams for that whole thing is estimated at 72 using lower left, and then the total milligrams using upper right is 224. So then it tells you to average. And what's the average of those two? 296, is that right? So 150 minus 2, 148. That's why you get 7 attempts. Is milligrams. So each of these numbers is what? These red numbers? What are those?
Meters. Milligrams.
This is the rate. These are rates, right? This is our rate function. These values in the table are the multivariable function. The dependent variable is the rate. So what are the units of the red values?
Milligrams per square.
Milligrams per meter square, that's right. Milligrams per unit of area, those are rates, right? That's a rate. And then when we take each of those times a number of meters squared, we get the quantity, which is milligrams. Got it. So the trick here was don't look at the table and think that means upper right, lower left. You have to graph this because y decreases downward in the table, so that flips it. Okay, questions on this example? So that's a good application of what we did last time. What else? Okay, so now they're not using upper or lower, they're not using any of the corners, but they're just giving you a value. What are these? There's some of them. S33. How are you supposed to do this without these values? Oh, right, the contour lines, of course. Okay, so 2, 3, this is a contour line of 3, 4, 5. Okay, and you have to figure out what that one is. All right, so here it's not using corners. You don't have to use corners. That's just a systematic way of doing it, right? Like we always, like in Calc 1, we'd always use the right side of the intervals or the left side of the intervals to get the function value. So this is just a different way. You can pick any point in every piece of the partition and just let whatever the function value is, the rate is, be the rate for that whole thing. So they're just jumping around here. So consider this whole rate of change to be 2 here, this whole rate of change in this one to be 3, 4, etc. And then you find the other ones. So what is this? 5, 6, 7, 8. Is that 9? So then because you're using that point right there, you assume that that part of the partition right there has a rate of change of 9. Is it 10? This is 4, 5, 6, 7. Yeah, right, 10. But then you do it the same way. You do this through rate times. In this case, each one is just 1. Every dA is just 1. So I think you end up just adding up the different rate values because you multiply them all by 1 anyway. Oh, but then your G is plus 5. This is showing F, and you have to add 5 to all of them. So if G is the rate function, it's all these contour lines plus 5. Question on that one? Okay, so yes, please.
For the notation, like S33, is the 33 referring to like the number of regions?
On the square S3, yes, it's referring to the partition, that in the X direction are partitioning into 3 intervals and Y into 3 intervals. Yeah. So it's not the fact that this is showing that X goes from 0 to 3. So you could go from 0 to 30 and 0 to 30 and still have S33, and then you'd have 10 by 10s. Yeah. Other questions? Okay, so let's look at this example here. So I've got we want to integrate. No, not this one. Too soon for that one. We want this one. Here we go. We want to have the gold is the function or the surface we're interested in is actually x plus 1. So that's z equals x plus 1. Okay, and then the region is, we're going to look at our region is from, x is from 0 to 4. and y is from 1 to 3. So I'm showing that here in R2. I'm also showing it in the R3 perspective here. And we know that R3, things are rotated 90 degrees, right, from our standard. So those two blue regions are the same region. Does everyone see that? Those are the same region, right? Because in R2, x goes out to the right, and y is up. But in R3, it's kind of like x is toward us, and y is to the right. So again, you got to take, right, you're taking that, and then you come and you put it like that, right? So those are the exact same region. And so we want to look at what would it mean, what would the meaning of this expression be? So what would the meaning of that be? So if I'm doing the double integral of this function, the gold plane, x plus 1, into evaluated over that blue region, x from 0 to 4, y from 1 to 3, what would that give? First of all, would that give a function, an expression, a value? What will it give? Most people are saying a value, right? They'll give a value, okay? What will the meaning of that value be? Yeah, Richard. What's that? Volume. What volume?
Volume underneath fxy in that rectangular region.
Okay. See if I can draw it here. So it's the volume from the surface to the xy plane. This is the key. It's from the surface to the xy plane, right? Will you always get a volume when you do a problem like this? Whenever you do a double integral of a surface, there's always be a volume. Matthew, why not?
Because you can have a function that can be accumulating some of the value, besides volume.
Oh, okay. So we're talking about, okay, if we're talking about the geometric perspective here. So will it always be straight up volume? Yeah, so what we want to say is signed volume, meaning if that surface, over our region, the blue region, if that surface ever does what? It ever cuts below the xy plane and carves out some space below the xy plane, that volume, what will happen to that? It'll get subtracted. It'll have a negative contribution to the value of the double integral. So that thing gets subtracted from whatever regions the surface is above the xy plane over our region. Okay, so any spaces over the region above the xy plane have a positive contribution. Any spaces where the surface comes and carves out space underneath the xy plane will have a negative contribution. So this will always be signed volume, meaning a difference of volumes or net volume, okay? But in this case, the surface is always positive over our region. So we truly get volume. Okay? So before we actually evaluate the integral by calculus, this is a volume we can just calculate by geometry. So we're going to do that first. So what is the volume of this thing? So this is what y goes from 1 to 3. And x goes from 0 to 4, and this surface is z equals x plus 1. So any way you can, the easiest way you can, find the volume of that. Does all the red show up? Oh, pretty good. Okay? Any way you can, the easiest way you can, okay? So Make it as easy as you can on yourself. Find the volume of that thing I outlined in red. Go. Let me give you a hint. So I'm giving you a hint here, right? Outlining part of it. That part of it has a volume of what? 8. 2 times 4 times 1, right? And then we got the rest up here. We'll call that still in red, so I'll do it in red. Volume 2. What's our z coordinate up here? That's 5 up there. Can you read that? What's the z coordinate here? 1. So now we should have it, right? 4 times 5. 4 times 5 times a half times. No, you start at 1, right? This is starting at level 1. Z equals 1 up to 5. We already took care of that part down there. So this is 4. 4 times 4. Did I say 5? Okay. So it's like, no, it's not 5, you guys. 4, or what? So 1/2. 4 times 4 times 2 equals 16. Volume is? So that's using geometry of large solids, right? So that's what if we evaluate the integral. If we evaluate the integral, we ought to get 24. So how do we set that integral up? We're going to integrate. So our function is x plus 1. Because we have a rectangular solid with just all constants, you can either order is fine. So we could do dy first and then dx, or dx first and then dy. If we do dy first, that's our inside integral. That's our inside integral. Y goes from 1 to 3. So that's the dy integral is going to be our function. Antiderivative with respect to y evaluated from 1 to 3. Then we're going to get, that will be a function of, what will our resulting function be a function of? X. So we should, all the y's will be gone after that, and we'll have a function of x, and we'll have a straightforward single integral. Dx goes from, or x goes from 0 to 4. Go, do it. And we're expecting to get 24. What did I do wrong?
It's 2x.
2x plus 2x. All right, did you get 24? Okay, and this is looking at double integrals what from a geometry lens. On R3, the geometry in R3, right? It gives net volume, difference of volumes, or signed volume, right? Any of those three terms. Okay. We also know if this function, if we're looking at rate and accumulation, then this function is what kind of function? It's one of these rate functions with two independent variables, right? Two independent variables, like our snow on Monday, and then you had a couple examples in the homework, okay? So just note that. And then we're still accumulating the quantity, but now over two independent variables. So one independent variable x, one independent variable y. So make sure you see these double integrals in those two lights, right? Accumulation at a certain rate, and geometry, meaning difference of volumes or net volume in R3, formed by the surface and the xy plane, right? Questions on this example? So, and then if we were to do, we won't take the time, but if we were to, we could easily, with these constant limits of integration, we could easily integrate x first, and then y, but then you need to evaluate from 0 to 4 first, and then 1 to 3, and you can do the math, you'll get 24, okay? So when you have these rectangular regions, what we call the order of integration is just interchangeable, right? You can just change the order of integration without any, seamlessly, right? There's nothing to consider, you just can change it. Questions on this example? Okay, so let's look at non-rectangular regions. Non-rectangular regions. That's this one. Okay, so now again I have the surface 2 plus 0.6 cosine x sine y. And I'm going to integrate that over this region. The top, the bottom of it here is, this is y equals 1/2 x. And the top is 4 minus 1/2 x. Okay, and if I do this double integral over, so this is my r. Actually, we're going to call that, so we're going to start calling those d. So a curve, a one-dimensional curve is going to be c. Our two-dimensional regions are going to be d. And our three-dimensional solids are going to be E. So this is D. Okay, so we're going to integrate over D, and we're going to integrate fxy. And what will we get? Expression, function, number. Expression, function, number. Number, right? Value. Okay, we're going to get a value. And what will that value represent? Which volume, Andrew?
Volume from the surface
So from the surface,
down to the XY.
the XY plane, down to the XY plane. Okay? Make sure you got that's down to the XY plane. And then laterally, it's defined by this region, right? The sides of it. The sides of it are defined by this. The bottom is the XY plane. The sides are defined by vertically from the region, right? And then the top is the surface. Okay? So that's what that volume is what this thing would calculate. Okay? So how do we do that? So suppose we're going to look at, so this is 2 plus 0.6 cosine x sine y. Okay, and so we want to look at this thing from, we're going to do dy dx. And so now when we start getting into non-rectangular regions, we want to really think about what this means. So dy would be, how do we consider x when we're looking at this thing with respect to y? We consider x how? As a constant. So we can just take a typical x value right here, like this. So this is just x, and we're going to hold it constant. Okay, hold constant. And we're going to integrate what from where to where? With respect to y. From there, and then we're going to accumulate little bits as y changes, right? Up to there. So for a given a constant x value, this inside integral is going to be like a strip. It's like we're going to be like accumulating a strip, a vertical strip from what? Bottom to top. And then we're going to integrate bottom to top. That's what integrating with respect to y means. The bottom of the region, wherever the bottom of the region is, to top. So this is the bottom. Where's the bottom of this region? It depends on the x that you have, right? So it's 1/2 x. And then where's the top of this strip? It's the top y value, right? 4 minus 1/2 x. Okay, and then once we have that typical strip, then we say we're going to integrate with respect to x. So where's the first typical strip, or the leftmost typical strip? X equals 0. Well, that's what I'm showing, but I never told you that. So, yeah, so based on what this reads, so you'd have to be given that information. So I guess I'm giving it to you through the picture. So, yeah, so and then x would be from 0 to 2. Yeah?
Does it matter which way you do it for this one?
Let's talk about that and after we kind of do a little bit of work here. But yes, that's a good question. So this is the order of integration dy dx. This order of integration is, we're going to call this type 1. Type 1 means you do dy first, you do y first, and you x. In other words, first bottom to top for a typical vertical strip, and then left to right. You're gonna accumulate those strips from left to right as a second step. So dy dx is what we're going to call a type 1 double integral. And that's the idea of bottom to top, then left to right. Okay, so this is going to get ugly quick. We'll just do steps until we can't anymore. So what will our first step be here? What will we have? 2y plus 0.6 cosine x negative cosine y. Are we done? Is there more? I mean, to that antiderivative? No, we're good, right? That's the whole antiderivative. And then we're going to do that from half x to, and where will those numbers go? Into the y's, right? This was, we were integrating with respect to y. So we're going to put this in for y. And then we're going to put the 1/2 x in for y. And then subtract, right? So we'll just do that one step and stop. So we're going to have 2 times 4 minus 1/2 x plus 0.6 cosine x negative cosine of 4 minus 1/2 x. That's just plugging the top limit in. Minus 2 times, this is slightly easier, 1/2 x plus 0.6, almost done, cosine x times negative cosine of 1/2 x. 1, 2, 3, 4, end parentheses. Make sure when you subtract an expression of terms that all those are going to get this negative, right? That's going to get the negative, and that's going to get the negative. And then that's dx. And now this is pointless to go on from here. But we would, so what would you do? This is now a standard integral in terms of x. Get the antiderivative, and then evaluate from 0 to 2. And that final number that we get will be this volume, right? The volume from the yellow surface down to the xy plane, confined laterally by the region D, right? Like vertically, the vertical walls created by region D to do that. Is there a question? Okay, so now let's talk about type 2. Type 2 then is what order of integration? If this is type 1, then type 2 is dx dy, which would be, first we would go from
0 to 2.
left to right, and then bottom to top. So what would happen here?
X equals to something.
So type 2 would be dx dy. X is our left to right variable, so left to right. So what's the left side? X equals 0. What's the right side? 2y. And so we're gonna have the integral from 0 to 2y, and then from what to what? From 0 to 4. Is that right? Why not? What happens as we go from 0 to 4? So you say I get to here, up to 2. What's going on at 2? What's my left? The left is 0, my right is? Uh-oh, it's not 2y anymore, it's just 2. And then when I get up here around 3, 3.5, my left is 0, my right is? Whatever this is, solved for x, right? So something's going on here. Our right boundary is changing for different y's, right? So what would that mean? If we were to do type 2, you've got to break it up into 3 double integrals. Do you see that? We're not going to do this one, guys. Don't worry. You'd have this. The first integral would be from what, 0 to 2y, as y goes from 0 to 1, and then your second would be x goes from 0 to 2 as y goes from 1 to 3. And then your last one would be x goes from 0 to whatever this y value is as y goes from 3 to 4. So in order to get something equivalent to this single type 1 integral, we would have what? A sum of 3 type 2 integrals. So let's do an easier example of that. Any questions on this example? Okay, so here's an easier example of that. Let's look at this one. So this is ln of x. Our region is this curve is ln of x. And then this is y equals 1. And this is x equals 0. And this is y equals 0. And then there's our function. Okay, so let's do a type. Let's set it up as type 1 and type 2. Ready? Type 1. What's the order of integration for type 1? dy dx, which means what first? Bottom to top, right? So bottom to top. So what's the bottom of this thing? 0 is the bottom of this. Part the way, right? So here, so we're doing what type 1 is dy dx, or bottom to top, then left to right. So the bottom is 0, and the top is 1, when x also goes from 0 to 1, right? And that's for our function 1/5 e to the y plus 1/10 squared. And that was dy dx. But that's not the whole thing, right? That was just this much of it, where the bottom was y equals 0. So now what's the other one? So from bottom now over here is ln x, top is 1. And the bottom is ln of x when x goes from what to what? 1 to, don't guess, right? So what x value gives a natural log of 1? E, right? E. Okay, and so then when we come in both of these integrals, we come to what? We come to antiderivative of this with respect to y. What's the antiderivative of that thing with respect to y? Is it 1/5 times 1/3 e to the y plus 1/10 to the third? Well, then we're talking about antiderivative, right? Does it work? So if I took the derivative of this, would I get this? No, because of the chain rule, right? Because of the chain rule, I'll have another e to the y, which I don't have here. So this does not have a quick and easy antiderivative. Probably need a computer to do it in numerical method, okay? So we're kind of, not only do we have two integrals to do, but we're stuck here. We can't do the antiderivative. That antiderivative with respect to y is impossible. Let's try type 2. How about type 2? What's our order of integration for type 2? Dx dy, which means left to right, bottom to top. So here we go. What's the left side of this thing? X equals 0, right side? So we're going left to right. Will we need to double integrate, or we need to split it up in this case? The whole, for all y's, we have the same left side and the same right side. Do you see that? It's the same left and the same right for all values of y. So it doesn't require us being split up. So this is x equals what? The right side of this is x equals e to the y. So we're going to go, x goes from 0, this vertical here, 0 to e to the y. As y goes from 0 to 1, same function. I didn't draw it over here. Is that consistent? Kind of? Okay, so that's what that looks like over here. Can we do the antiderivative? 1/5 e to the y plus 1/10 squared. Can I get the antiderivative of that?
You distribute it.
No, look what we're doing with respect to x now.
So just
Just times x. So it's 0 to 1, x over 5. So the variable that you're doing an antiderivative with respect to makes all the difference. And that will be from 0 to e to the y dy. And now I get 0 to 1. E to the y will be e to the y over 5 times e to the y plus 1/10 squared. Oh, so actually I could have done it back here if I would have just foiled this out. We could do it with respect to y. We'd need to foil it. Do you see that? Yeah. So if you just FOIL out this binomial squared, then we could easily do this with respect to y, because you just have individual exponential functions. But what about now? Can I, if I don't FOIL it now I can do the chain rule, right? This works for the chain rule. Now I've got that e to the y I needed, right? I've got the e to the y I needed, so it would be, now I could do 1/3 times 1/5. I should have made it to the higher power. And this can be 0, minus 0, right? When you plug 0 in here, that just all goes away. So just all you need is the EY plugged in. So then we got it. Yeah, 1/15 e plus 1/10 cubed minus 1/15 times 1 plus 1/10 cubed. Did I make a mistake? Is it good? So sometimes this is what happens. In one order, you get, pretend this was a higher power, like to the 8th or something. But you'll get an antiderivative you can't do. But when you switch it to the other order of integration, now suddenly you can actually do it algebraically. You can get that antiderivative and work it through algebraically. And the other advantage to type 2 was it was one double integral instead of a sum of 2. Okay? All right.